A very good day, I bid to Dr. Maza. My name is Vanisri, and I'm from Group 3. We're here to present a report on an iron-based catalyst. So our industry of choice is Yara International, and then for my part here, I'll be giving a brief, I wouldn't say brief, a introduction to the company. As you can see here, we have the Yara International logo. So that is their company's logo. Yara International was established in 1905 and their headquarters is in Oslo, Norway. It is a widely regarded global leader in the agricultural sector. The company plays a very important role in sustainable farming by producing and distributing fertilizers and agricultural solutions that enhance soil fertility and agricultural productivity. One of the most crucial aspects of Yara's operation is the production of ammonia. So NH3, as you know, which serves as a key ingredient in nitrogen-based fertilizer. These fertilizers are essential for addressing the increasing global demand of food, uh, driven by the population growth, then need to maximize the agricultural output. The production of ammonia relies really heavily on the Haber process, which we explained more by my other group members. A global recognized industrial method that synthesizes ammonia by reacting with the atmospheric pressure of nitrogen N2 with hydrogen H3 under high temperatures and pressure. Now a little bit of key insight about the catalyst that will be used, which is iron catalyst. Iron catalyst is not only efficient but it's also cost effective, making them ideal for large scale users. Iron is readily available and inexpensive compared to other catalyst materials, and it performs readily under high temperature and high pressure conditions of the Haber-Bosch process. This catalyst is fundamental in achieving industrial scale ammonia production, meeting the needs of global agriculture. Iron catalysts combined with promoters such as potassium and aluminum oxide, which can optimize its reactivity and longevity. This ensures consistent ammonia production, which helps Yara deliver high quality fertilizer to support farmers worldwide. In this slide, you can see Yara has recently intensified its efforts to produce green ammonia, which also will be explained more detail by my other group member. This is just a brief introduction to it. Green ammonia not only aligns with the global climate goals, but also positions Yara as a leader in a sustainable innovation. The iron catalyst remains a cornerstone of this transition, continuing to play an important role in enabling efficient and sustainable ammonia production. The company's commitment is advancing catalyst technologies and developing green ammonia underscore its leadership in the fertilizer industry and contribution to building a more sustainable future. Thank you from me. So now my next groupmate will present the rest.
Hi. The type of catalyst used in the Haber process is called magnetite-based iron catalyst. In this part, I will compare between the basic catalyst and other type of catalyst used in the Haber process. First, we compare between two types of iron catalyst. First, magnetite iron catalyst, second, classic iron catalyst. The similarities between them is that they are both heterogeneous catalysts, and at the same time they use promoters like the potassium and aluminum oxides. However, the differences between them is that first, the structure formulation for magnetite iron catalyst is depending on the derive of Fe3O4, and the advancement structure used in the preparation. However, the classic iron catalyst is lack the formulation advancement. However, it was considered to be durable and more reproductive at the time of Haber and Bush. Second, we compare between magnetite iron catalyst and cobalt iron catalyst. So, similarities between them both aim to improve the efficiency of the ammonium production and are promoted with additional components to enhance performance. However, the differences between them is that the cobalt modified catalyst is incorporated with the cobalt to significantly boost volumetric activity, approximately doubling it compared to the standard magnetite catalyst. However, the magnetite-based catalyst remain more efficient and is more accessible, particularly for standard industrial applications. Third, we compare lastly between magnetite-based iron catalyst and pre-reduced ammonia catalyst. The similarity between both of them is that both contribute to the enhancement of ammonium synthesis by improving the operational efficiency and reducing the downtime. However, the difference between the both catalysts is that the pre-reduced catalysts are processed off-site to eliminate the need for extensive in-situ reduction during the startup, which significantly reduce the initial energy consumption and feedstock waste. But for the magnitude-based catalyst, it's efficient. However, it requires an on-site reduction process before achieving the optimal performance.
Activity refers to the ability of a catalyst to increase the rate of a chemical reaction. A catalyst with high activity enables a reaction to proceed rapidly even under moderate conditions. The activity of iron catalyst is crucial for facilitating the dissociation of nitrogen molecules N2, which is a highly energy-intensive step due to the strong triple bond in nitrogen. Iron provides an active surface where nitrogen and hydrogen can absorb, react, and form ammonia, which is denoted to NH3. Activity is ability to favor the production of ammonia, NH3, while minimizing the formation of undesirable byproducts such as molecular hydrogen H2 and nitrogen N2 remaining unreacted or forming alternative compounds. The Haber-Bosch process operates under high temperature, which is 400 to 500 degrees Celsius, and pressure 150 to 200 atmospheric pressure. Under these conditions, the iron catalyst selectivity ensures the reaction between nitrogen and hydrogen primarily leads to the formation of ammonia rather than the other less useful compounds. Stability refers to the catalyst's ability to maintain its activity and selectivity over time and under operational conditions. In the Haber-Bosch process, the iron catalyst operates under extreme conditions of high temperature and pressure. Its stability ensures consistent ammonia production over extended periods. By balancing thermal, chemical, and mechanical stability, the catalyst achieves durability in the harsh operating environment, ensuring its role as a key component in large-scale ammonia synthesis.
Here, in classification, we have two classifications for the magnetite iron-based catalyst, which is first, heterogeneous, second, fused iron catalyst. It is classified as a heterogeneous catalyst because the reaction taking place in different phases than the reactants. In Haber process, the reactants are in the gaseous phase, which are nitrogen and hydrogen, whereas the catalyst in solid phase. Additionally, it's also considered as a fused catalyst, where the catalyst is combined with other substances called promoters. The original Haber process used the additives which are potassium oxides, aluminum oxides, and calcium oxides.
Hi, I'm Afina. We explain about mechanism of catalytic or ammonia synthesis in Yara International Company. Yara International used advanced ion-based catalysts in the Haber-Bosch process to efficiently synthesize ammonia by reacting nitrogen and hydrogen gas at higher temperature and pressure. The process began with the absorption of nitrogen and hydrogen onto a magnetite catalyst surface. Promoter like potassium oxide enhance the catalyst's ability to weaken nitrogen's strong triple bond, allowing it to dissociate into atomic nitrogen. Hydrogen also dissociates into atomic hydrogen. This atom then fused in stepwise hydrogenation to form intermediates such as NH, NH2, and finally ammonia. The ammonia is then released and the catalyst surface is renewed for further reaction. Promoter play a key role by stabilizing intermediate, improving absorption and lowering energy barriers, especially for the rate limiting step of nitrogen dissociation. This reduces activation energy, speed up reaction, and maximize ammonia yield. Understanding this mechanism enables improvement in catalyst design, making ammonia production more efficient and sustainable. For 3.2, ion catalysts like those used by Yara International in ammonia synthesis are designed to perform under the harsh condition of the Haber-Bosch process. The main component is iron, which is typically sourced from magnetite, which is reduced to metallic ion during the activation. Metallic ion provide active site for the dissociation of nitrogen and its subsequent reaction with the hydrogen. To enhance the catalyst activity and stability, several promoter and structure additives are incorporated. Potassium oxide is a key promoter that increases the electron density on the iron surface, making it easier for nitrogen to absorb and weakening its strong triple bond. This reduces the activation energy required for nitrogen dissociation, the rate limiting step in ammonia production. Potassium oxide serves as a structure promoter, improve the catalyst mechanical and thermal durability to withstand higher pressure of 50 to 25 MPa and temperature of 400 to 500 degrees. Silica and alumina, often present in trace amount, adds a structure support to prevent ion particles from sintering, maintaining at higher surface area and activity. For the catalyst depletion process is precise. Raw materials are carefully blended and calcined to ensure uniform promoter distribution within the ion matrix. During the activation, the magnetite is reduced in hydrogen-rich environment, forming thinly dispersed metallic ion with promoter embedded on the surface. This design is maximize the interaction between nitrogen, hydrogen, and the active site while minimizing the activation caused by impurities like oxygen or sulfur. Over the years, the composition of ion catalysts has been optimized to balance high activity, durability, and cost-effectiveness. While plutonium-based catalysts offer higher activity, they are expensive and prone to deactivation, making them unsuitable for large-scale use. In contrast, the ion-based system remains the industry standard due to its strong performance and well-researched promoter effect. By maximizing ammonia yield and reducing energy consumption, this advancement aligns with sustainability goals in modern chemical manufacturing. So that's all from me, and thank you.
Hi, I'm Faisal Hakim and I'll be talking to you about the environmental benefits of using iron-based catalysts for ammonia production. But before I get into that, I would like to highlight the detrimental effects of the carbon Haber-Bosch process to our environment. So the Haber-Bosch process, very common for ammonia production, is responsible for over 450 million tons of carbon dioxide gas emissions into our atmosphere, which accounts for over 1.4% of global emissions annually. This Haber-Bosch process is also very energy consuming due to its high temperature and high pressure nature. It consumes about 1% of global energy production, which also hastens its carbon footprint. So the reason why iron-based catalyst is better for the environment is because iron-based catalyst doesn't require temperatures as high as other catalysts. For your information, other catalysts used for ammonia production requires a temperature around 400 to 500 degrees Celsius, which is pretty high. Unlike iron-based catalysts, as you can see in the graph, ammonia production with iron-based catalysts can be seen at temperature as low as 100 degrees Celsius, and it's higher at 180 degrees Celsius, which is still considered low if compared to 400 to 500 degrees Celsius. This low energy consumption will save energy and reduces the carbon footprint of the Haber-Bosch process. Additionally, most studies have proven that iron-based catalysts will help in reducing the greenhouse gas emissions. This is because iron catalysts will help in the production of green ammonia, where the reliance of the heavy waste process towards fossil fuels, which is the main fuel source for the heavy waste process, will be reduced. So it will reduce the greenhouse gas emissions, it will reduce the carbon footprint of the heavy waste process, making the ammonia we produce much greener to the environment. Iron-based catalysts, like I said earlier, also helps in enhancing the energy consumption of the heavy waste process, thus saving more energy